Hello, and welcome to your last video in our solutions unit. So you want to access pages 446 to 451 in your textbook to get some more information on colligative properties. Just realize that we only need to understand these at a qualitative level. And so I'm going to be sharing my voice again and let you get some good information down.
We're going to continue to talk about solutions and their properties in this lesson. These properties in particular depend on the concentration of our solute particles, but not necessarily their identity. So if we understand how our solute particles are dissolving and even perhaps ionizing, we'll be able to tell what kind of colligative properties are going to be present. Don't let that term throw you off too much. It's just a fancy word for properties that depend on the concentration of our solute particles. There are three colligative properties that we have to understand when it comes to solutions. They are boiling point elevation, freezing point depression, and vapor pressure lowering. Let's look at one at a time. Boiling point elevation. What this means is compared to just say a sample of pure water, when we mix some type of a solute into our pure water, we are going to have the colligative property of boiling point elevation. We're going to take that original water's boiling point of about 100 degrees Celsius and increase it by some certain amount depending on what we put into our water. The example that you have on this slide is when we have 50% antifreeze that you might add into your car systems. When we add in a 50% antifreeze solution to our cars, we can increase the boiling point of the water that would have been 100 degrees Celsius on its own. Will now be around 105 degrees Celsius. Why that is because when we have a greater number of dissolved particles in our solution, those particles that have dissolved are going to block the solvent gas from escaping. So remember, when we want to boil things, we want to turn them from a liquid into a gas. If we have a lot of things in our solution blocking the way for those solvent particles to become gases, it's going to take a higher temperature in order to boil them away. Oppositely, freezing points are going to be lowered. We call that freezing point depression. Much the same reason, but this time our greater number of dissolved particles are going to actually disrupt our crystalline structure from forming when we freeze something. This is going to make it require a lower temperature in order to freeze. When we put antifreeze in our car, what we're doing is we're taking that freezing point of water on its own at about 0 degrees Celsius. We can actually get that freezing point to decrease to negative 40 degrees Celsius, which is good because we have pretty cold weather here in upstate New York, and we don't want our motors to freeze up. Vapor pressure lowering is our third colligative property. When you think about it, our vapor pressures are measuring the amount of particles that are above our liquids as gaseous particles. So how does this get affected when we put in solute into a solution? If you look at the picture, those purple solute particles mixed in with the water are actually blocking the way for some of those water molecules to escape as a gas. So this one is very similar to the boiling point elevation, but essentially what we're saying here is the greater the number of dissolved particles we have in a solution, those blockings are going to happen more frequently, and we're going to have fewer gas particles being able to escape. And when we have fewer particles up in the gaseous stage, we have a lower vapor pressure. Some particles are going to be more effective at creating these colligative properties than others. It all depends on how they dissolve. But essentially, the number of particles that result during the dissolving process will increase the effect of the colligative property. So if we have more particles dissolved, it's going to increase the boiling point even more. It's going to decrease the freezing point even more, and it's going to lower the vapor pressure of our solution. So if we look at these examples that we have on this slide, CH2Cl2 is an example of a polar substance. Bonding is coming back. Now remember, our polar substances, they will dissolve because of our rule, likes dissolve likes. But when they dissolve, they do not dissociate. So CH2Cl2 is going to show one dissolved particle compared to if we didn't have any dissolved in our solution. So when I say one dissolved particle, I mean for every particle of CH2Cl2 that dissolves, there's going to be one particle dissolving. We could have a lot of particles in there, but it's a 1-to-1 ratio. So it will elevate our boiling point and decrease our freezing point and decrease our vapor pressure, but it's not going to do it quite as much as some other things. If you look at KBr, for instance, that is a soluble ionic compound. When it dissolves, it breaks up into K1 plus and Br1 minus. For every 1 KBr we put in there, we get 2 dissolved particles. Those are going to be more effective at increasing our boiling point and lowering our freezing point and lowering our vapor pressure. If we look even further, something like calcium bromide, now that formula, CaBr2, shows us that we're going to have it dissolve into 3 particles because it ionizes as well. We're going to get 1 Ca2 plus cation and 2 Br1 minus anions dissolving for a total of 3 dissolved particles. That means CaBr2 is going to have an even bigger effect than the other 2 examples we went over. So when you think about it, which compound would be the best at salting the roads in the winter and why? Well, if we had to choose between these 3 things, we might choose CaBr2 because it will lower the freezing point even more. And that means that our ice is not going to be out there when we're trying to get to school in the morning. Now, there are other factors, of course, that determine what kind of salts are put onto the road. But if we were just looking at the effect on the colligative property of freezing point depression, we would choose calcium bromide. When we look at things like sodium chloride, magnesium chloride, or aluminum chloride, though, which one of those would we put on our roads? Well, if you look at all of these choices, you're going to see aluminum chloride is going to dissolve into more particles, 4 to be precise, an aluminum cation and 3 chloride anions for every 1 compound of aluminum chloride that we would put on the roads. So in this instance, you might pick the aluminum chloride. Now the concentration of the solution also is going to come into play. So if we have a higher concentrated solution within a certain limit, it's also going to have a bigger effect on these colligative properties. Again, just keep in mind, the more particles we have dissolved, whether that's because they break up into more particles or because we happen to have a higher concentration of solution, the bigger the effect we'll have on these colligative properties. This slide is just showing an example of how antifreeze works in our cars. And you can see that it's not something that you can predict very easily in terms of how much it will lower the freezing point. It depends on the percent of antifreeze you have per volume of water. So to answer our first question here, what is the best concentration of antifreeze to make the most effective solution for use in cars? Well, if you read the graph, you'll see that it dips down the lowest at about 67% concentration. Now, even though this solution is called antifreeze, we still use it in our cars, even in the summer. And why is this? Well, because not only does the colligative property of freezing point depression come into play, we can also elevate the boiling point of our fluids in our cars. And so the cars won't boil off the liquids that they have on hot days. So both of these come into play when we are using antifreeze in our cars.
Okay, so hopefully that gave you some insights on colligative properties. The last little thing that we want to mention here is that we can have heats associated with making solutions. And we'll dive more deeply into this in our next unit on energetics. But what we have to be able to see here is that using a table like the selected heats of reaction that you see on this slide, we can predict whether making a solution is going to result in heat given off or heat being absorbed. So if you look, all of these reactions that we have here, I'm calling them reactions, but it's really a physical process where we are showing the solid of these substances, what happens to them when water is added, and they break apart into their ions because all of these examples happen to be soluble ionic compounds. What you need to be able to do is to look at these numbers on this table and tell whether that process is going to be endothermic or exothermic. And you can see, it kind of tells you underneath here, but we should also know that a negative change in our heat means that we're going to have an exothermic process, and a positive means that we're going to have an endothermic process. Now you can check out pages 415 to 416 in your text for some more guidance on this concept. But I also liked this picture here. It kind of shows you that there are different energies at play when we're dissolving our substances. So really, we are looking at the energy involved in separating our solvent and our solute from their own particles, and then rejoining them into solution and comparing how those energies affect one another. Basically, what you need to know is that if you have a negative delta H, that means that the dissolving process is exothermic. Energy will be released when those substances dissolve. The solution temperature, because that energy is being released as a product, will go up. And I know that students still struggle with what's the system, what's the solution, what's the surroundings. Well, with solutions, it's kind of all happening in one container. Think of the dissolving process as the system, but that solution itself, which has a lot of solvent particles as part of the surroundings, really is the surroundings. So if we have an exothermic process, that solution is going to experience an increase in temperature. Oppositely, a positive delta H means that the dissolving process is endothermic. Energy is absorbed from that dissolving process. So it's on the reactant side, and the solution temperature will decrease. It's going to get that excess energy from the surrounding solvent particles. Again, the solution itself will decrease. It's kind of a combination of the system and the surroundings all in one container. If you keep the idea of that process being the system, then that should help clarify some of these issues of energy for you. All right, so I hope that that was helpful. That's all I have to say about solutions. We're going to just continue to get our practice, and we will assess when our packet is finished.